All right, so we'll go ahead and get going. So as I said a few moments ago, welcome to the webinar series. In case you haven't seen me for a while, I'm Dr. Brian Kloppenborg. I'm the Executive Director of the AVSO, and it's great to see you all here today. And today we're going to talk about how citizen scientists can contribute to deciphering binary star systems. But before we go and get going with that, I have a couple of quick announcements. The first of which is if you haven't been on a Zoom webinar before, there's a couple of different controls than what most people see. So if you take your mouse and you wiggle it near the bottom of the screen, the menu that you see here will come up and it'll allow you to interact with us in a variety of different ways. First of which, you can use the chat button on the left-hand side to bring up the chat dialog box. And please, if you can, go ahead and introduce yourself in the chat. That's where I've been reading people's names and their locations, and it's wonderful to see you all there. In the middle is the question and answer box. So if you have a question for either myself or the speaker during the webinar, please put it into that Q&A box. Don't worry about interrupting the speaker. It appears in a queue from our side, and so Pierre and I can walk through that near the end of the webinar and answer your questions. And lastly, there's also an automatic closed captioning button there. And so if you do turn on closed captioning, the only thing that I need to mention there is that you should pick the language that's being spoken. And today it's going to be a mixture of American English and British English. And next, I'd like to just express gratitude to our 2025 webinar series sponsor, Voice Astro. Voice Astro provides online astronomy education, observatory resources, and research experiences to students and schools to perform observations, conduct research, and publish results. Please check out their website at voice-astro.org to learn more about their offerings in astrometry, photometry, and spectroscopy. I'd also like to mention that support from our sponsors like Voice Astro and donations make the work of the AVSO possible. To support the AVSO, please consider making a donation by scanning the QR code that's shown on your screen or by going to avso.org/donate now. All donations are tax deductible in the United States, and they support our mission to enable anyone, anywhere to participate in scientific discovery through variable star astronomy for now and generations to come. And now it's time for our main presentation. Dr. Pierre Maxted is an observational astronomer at Keele University in Staffordshire, England. He has expertise in discovery of characterization of binary star systems and extrasolar planets. From 2003 until 2020, he participated in all aspects of the Wide-Angle Search for Planets, or WASP. He participated in hardware development activities at the WASP South site in South Africa to follow up observations of the planets that were discovered with this instrument. He has been a member of the science teams for the KOPS mission since 2017, and he wrote the PI-KOPS data analysis software package that's used by the KOPS science team to precisely measure the size of planets orbiting nearby stars. He is a member of the PLATO stellar science team with responsibility for finding eclipsing binary stars suitable for testing the stellar models that we will be used to characterize planetary systems discovered by this mission. And so without further ado, I would like to turn the floor over to Pierre. So Pierre, you're welcome to share your screen.
Thank you. Good evening, everyone, or good morning, or good local time of day. Let me just get the things set up here, and then we'll get going. So I need to click play there. Are we seeing the right screen, Brian? Is that okay? Or have I got the right one?
Not yet. I think you'll probably have to, on the share screen dialog, you have to click one additional button there.
Yeah. Yeah, there's the share sound.
All right, so we see your desktop with PowerPoint open, and we see your slides. So the floor is yours.
Fantastic. Okay, so let's crack on with it. What I will talk about today is eclipsing binary systems, what they are. I'll give you a little introduction to why eclipsing binaries are so interesting, why I like to study them, the sorts of measurements we can make with them, and there's a wide range of eclipsing binary stars, but I'm going to focus on detached eclipsing binary stars, well-separated stars for reasons I'll explain. And then I'll also talk about the European Space Agency PLATO mission, what it aims to do, and how eclipsing binary stars, why they're part of that mission, why they will help the PLATO mission to achieve its aims. And that will lead me into how citizen scientists, like members of the AVSO, can help us with that. So that's the plan. I think I need to set some expectations first. If we're talking about binary stars, because binary stars produce some of the most extreme and amazing phenomena in the galaxy. We have massive stars with colliding winds and cataclysmic variable stars that go nova and have mass transfer, and massive contact binaries that will merge and produce weird supernovae, and these sort of RS Canven type very active X-ray active stars. But we're not going to talk about any of those things today, because what we're interested in is calibrating the properties of normal stars. So we're interested in detached eclipsing binary stars, ideally systems like this particular one, which I've studied, AI for Nexus, where you have two stars that are very well separated, meaning that they are minimally affected by their mutual gravity. There's very little interaction between them. So what we're interested in doing, what we use these detached eclipsing binary stars for, is to make accurate and precise measurements of the fundamental properties for normal stars. And we need those measurements of properties like the mass, radius, and luminosity of normal stars to calibrate stellar structure models. These are the computer models that have the physics of stars built into them, so that we can predict how old stars are, how stars will evolve, and so on. And I think the important point to emphasize here when we're talking about normal stars is that since the discovery of 51 Pegasi 30 years ago, and because of missions like the Kepler and TESS missions, we know that normal stars means planet-host stars. It's now not a surprise to think about a star like the sun having planets going around it, around them, having a planetary system around a star. So normal stars, planet-host stars, I will use those interchangeably because they mean the same thing nowadays. That certainly wasn't the case when I started my astronomical career more than 30 years ago. But that's what we think of as being normal now for stars, is to have planets orbiting them. Okay, so there's this very nice tool that is available online as an educational resource, which if I click on that, you can see the animation going. So this is a tool where you can, this is a fairly simple but quite accurate picture of what happens when two stars are orbiting each other. In this case, these are two quite hot stars. The animation is obviously speeded up, but in this case, this is a binary system called V526 Sagittarii, where the two stars go around each other every 1.9 days. Binary stars can orbit each other with periods. For compact stars like white dwarfs, they might go around each other every few minutes. For normal stars, they might go around each other every day or so, and that orbital period can obviously be a lot longer, up to tens or hundreds of days. In the top right panel here, we have a black line, which is the computer model. That's actually, you might find that a little bit tricky to see, but there are actually some dots on that graph, and those dots are measurements of the brightness of the star at different times. Those observations might have been taken over several years, but once we know the time between the eclipses, that's the orbital period, the sort of repetition time of the orbit, we can plot the points as a function of the orbital phase. So we stack all the primary eclipses on top of each other, and naturally the secondary eclipses stack on top of each other. So the primary eclipse being this dip in the light curve when the hotter star is covered up by the smaller star, and the secondary eclipse here when the cooler star is covered up by the hotter star. And the shape of these eclipses, the depth, the width, the location are related to the properties of the star. So this is why eclipsing binaries are so useful, because that light curve contains information about the geometry of the binary system and the relative flux contributions of the two stars. So there's a lot of information to be gotten out of a light curve. We can see precisely, it's worth thinking about what that information is. What are the features of the light curve that you can measure, and how do they relate to the geometry? I've thrown a lot of equations at you here just to show you that there is an equation that's relatively simple that relates the characteristics of the light curve to the measurable, to some of the properties of the star. So the types of things we can measure is how long the eclipses last. If you have a nice total eclipse like this, you can measure how long one star hides behind the other, the duration of that occultation. You have the depth of the eclipses as well. Those quantities can be measured, put into an equation, and the quantity that you get are what we call these fractional radii, or the fractional radius of the star. So the information in the light curve, like this, is how big the stars are relative to their separation. There's quantity A, formerly known as the semi-major axis of the orbit. In a circular orbit, you just think of that as the separation of the stars. And the point here is, yeah, there's things you can measure in a light curve that directly relate to a fractional radii of the stars. So we have a powerful way to measure that. That nice blue curve looks like a textbook example of a totally eclipsing system where you have a smaller star going behind a bigger star at the secondary eclipse. Some of the keen-eyed observers here will spot that there's some curvature at the bottom of the primary eclipse as the smaller star scans across the face of the larger star. That's an effect known as limb darkening. I'm not going to talk very much about that. It is something I've studied extensively over the past few years. The reason I've studied it extensively is so that we know exactly how that works for the type of stars we'll be talking about today, solar type stars. It's now a very well understood phenomenon, so it doesn't add any uncertainty to our measurements. The thing that has really revolutionized the study of eclipsing binary stars is the quality of the data that is now available for us to study. Because of the requirements to pick up the faint signals from exoplanets, the instrumentation that's been developed, the observing techniques that have been developed, the spacecraft that have been launched, produce amazing quality data. And this is an example of that. These are real data. This is not a model. These are observations observed for a real star, HD 5876, obtained by the TESS mission. And I've done very little to these data. I've essentially just downloaded them, measured the orbital period, phase folded it. I've taken the average in phase bin, but you can see that you can more or less, print this out and measure those quantities that we discussed with a ruler and get the radii out. So this is a real theme for binary star science, eclipsing binary star science, because when you throw this sort of instrumentation and techniques that have been developed to study exoplanets at binary stars, the quality of the measurements we can make, the precision and accuracy of the measurements we can make are almost an order of magnitude better than what we could do 20, 30 years ago. So this has been a complete game changer for us. When you have data of very, very high quality, what starts to become an issue is not the data quality itself, but the sort of assumptions that you make in the analysis, and it really sort of tests it's a sort of real stress test for your analysis technique. So we're still using some of the software that was written, 40, 50 years ago sometimes for analyzing these binary stars. So to understand sort of what the limits are in terms of how far can we push these measurements of the radii of stars. When this light curve turned up for this really nice system, AI Finexis, AI Phi, I sort of noticed that TESS had observed this well-known eclipsing binary star, which was a real sort of showcase for what you could do with eclipsing binary stars when it was first studied in detail, maybe 40 years ago. I basically emailed all my friends in the binary star analyzing community and says, look, download the TESS light curve and do your analysis on it, and let's compare our results and let's get an idea of how well we agree with each other when we independently analyze these data sets. That turned up a few technical issues that got sorted out. The main results are sort of shown here on the panel here on the right, where these fractional radii that we can measure are compared. These are all different analysts using different models. There's a couple of more different sort of assumptions I made in the analysis here to do with the way that I handled the data. But you can see that these measurements agree really well with each other. There are some issues here to do with the estimate of the uncertainties, like the size of these error bars. Some of the methods that have been used in the past to estimate error bars clearly aren't up to it. They underestimate the error. That's been a long-standing problem. But the more modern techniques that have been developed again for exoplanet analysis do give us reliable estimates of the uncertainties on these measurements. And so in terms of how precisely you can measure the fractional radii, when you have good quality data like this for a bright, a bright eclipsing binary star with well-defined eclipses, you can get down to the 0.1% level. It's really quite amazing. It's like I said, it would have been unthinkable 30 years ago. And it's sort of the data is just sitting there for free. It's amazing when I think of the people I worked with when I started as a postdoctoral researcher. They used to have to go out to the other side of the world and sit on top of a mountain for weeks at a time to try and get data where you could measure the radii to 1%. And now you can just download a light curve and analyze it and get down to 0.1%. We're really very lucky to have this quality of data. Okay, so that's the fractional radii, but it's not an intrinsic property of the star. The other thing we would like to know is the mass of the binary. This is an animation showing two stars orbiting each other, being viewed, obviously not to scale, from the bottom. An important fact here to know is that if you have a star, like the sun, if you take its light and split it up in a spectrograph, you have the Fraunhofer lines. You have thousands of sharp lines in the spectrum, so well-defined wavelengths where there's less flux emitted because of the atoms in the atmosphere of the star absorb at that very well-defined frequency. You know, thousands of those lines across the optical range. And that means you can measure the redshift very precisely from the position or the apparent wavelength of those absorption features relative to their rest wavelengths gives you the Doppler shift, and hence it gives you the radial velocity of the star, essentially how fast the star is moving towards you or away from you. For eclipsing binary stars, we know that the orbital inclination is close to 90 degrees, meaning that the orbital plane of the binary is very close to the line of sight. So almost all that motion that we see towards or away from us, the sort of radial component of the motion is essentially equal to the actual motion. There's a very small correction for the tilt of the orbit. That's always got to be a very small tilt. And so the long and short of this is, particularly when you have very high quality spectrographs that are designed to measure the radial velocity Doppler wobble for planets, which is down at the meters per second level, if you apply that to binary stars, the signal is absolutely huge. It's really, really precisely measured. And so, okay, so with what we can do by taking spectra, pointing a telescope with a spectrograph at our binary star, we see two sets of lines, we see them moving around, and we can use that to measure the orbital speeds of the stars. So we have fractional radii from the light curve, and we have orbital speeds from a series of spectra. So when you put it all together, the light curve gives you the fractional radii. We have the orbital period from the time between the eclipses. We know that the inclination is very close to 90 degrees. We can measure it precisely, but that's all we need to know for now. The spectroscopy gives us the orbital speed. You can use speed equals distance over time. If you know how long it takes to go around the orbit and how fast the stars are moving, you know the circumference of the orbit, so you know the radius or the diameter of that orbit. You can then use Kepler's laws to relate the size of the orbit and the orbital period to the total mass. We actually have the mass ratio from how fast the stars move relative to each other, and so we get masses and radii. There are some equations for how you do that precisely on the right-hand side, but the long and short of this is that if for these detached eclipsing binary stars, we can get what they give us is direct model-independent, accurate mass and radius measurements for normal stars. And that's incredibly valuable. The fact that we have independently measured masses and radii that we can then compare to the predictions of stellar models. These are fundamental data that are used to calibrate our stellar models and calibrate our understanding of normal stars. So that's the theory. We can actually do a bit more than that nowadays. This is quite a complicated graph, but I'll go through it slowly. The total flux from the binary, essentially how bright the star is at different wavelengths. We know there's all sorts of all-sky surveys out there that have measured the brightnesses of stars at a variety of wavelengths. So, for example, the GALEX mission did an all-sky survey in 2 ultraviolet bands. The Gaia mission is a satellite that has been mapping something in the region of about 1 billion stars in the galaxy and measuring a lot of their properties, but in particular, how bright they are across the optical wavelengths. The 2MASS survey observed the whole sky at near infrared wavelengths. There's also some far infrared surveys. So we know how bright the binary star is. We know how much light is being produced, how much energy is being radiated and arrives at the Earth from the binary star, the combined flux of the 2 stars. We also have information from the depths of the eclipses in the light curve about the flux ratio, how much light is coming from each of the 2 stars. Ideally, this will be a system, a binary system, where you have total eclipses, in which case it's very easy to measure the flux ratio, because it's just the depth of that total eclipse, which is when you block the light from one of the stars, the light that's left over is the flux from the other star. So that's straightforward. You can also measure this in cases where the eclipses aren't total, if you have a model of an eclipsing binary star. The new thing over the last few years has been that the Gaia mission, as well as measuring how bright stars are, it also measures their parallax. This is the annual slight wobble in the position of the star that you see because you're viewing it from different angles from either side of the Earth's orbit. And this gives you the distance to the star. That's the new thing that has made it possible to measure the luminosities of eclipsing binary stars. Gaia, in fact, has completely revolutionized stellar astrophysics and our understanding of the galaxy because it has measured the distances and other properties of so many stars to such high precision over the whole sky. So we can combine those two things, how bright the star looks at the Earth and how far away it is, to actually get the luminosities of the two stars. And that we can do reasonably precisely nowadays. And that's a new thing that it was much harder to make that measurement, and it was much more model dependent before we had the data from the Gaia mission. So that's the luminosity. We tend not to think of luminosity. We tend to think what we typically quote rather than the luminosity is the effective temperature of the star. So there's a relationship between the luminosity of the star, how big the star is, and this number, the effective temperature. So we invert this equation to get a number for the effective temperature, which you can think of as sort of a surface temperature. Now, stars don't have a surface. They're, balls of plasma. Most of the light that you see is emitted from a sort of narrow region on the outside of the star, where the temperature is decreasing as you go outwards. But there is some characteristic temperature where most of the photons are emitted from, and that will be close to the effective temperature. So that has that's a very characteristic property of a star, its effective temperature. It determines whether it looks like, if it's a red star or a blue star. It will determine the appearance of its spectrum, whether there are strong hydrogen lines in the spectrum or whether you can see molecules in the spectrum. The effective temperature is something that has a very influential on how a star appears to us, and then vice versa. There's lots of things we can measure that we can then use to infer the effective temperature of the star. With the quality of the measurements that we have now for measuring the radii of the stars, and remember on the previous slide, we will know the radius of these stars if they're in an eclipsing binary. We know how far away they are, and we have, if we have lots of measurements of the flux and the flux ratio, as we do for AIP, it's feasible to get down to measurements of the effective temperature with a precision of about 25 to 50 Kelvin. And again, that's a factor of, that's an order of magnitude better than we could estimate the effective temperatures before. And it's direct and model independent again. So this is a new technique that was just being developed in the last, 5 or 6 years by myself and my PhD student, Nikki Miller. Very new technique. It's only been applied to 4 or 5 binary systems so far, but it's really valuable to have that extra information. They sort of solid measurements of such a fundamental property of the star as its luminosity, effectively how much energy is the thermonuclear fusion in the core of the star producing. Yeah, what makes this feasible is the Gaia mission. I think we should mention the fact that the Gaia mission has now come to an end. It observed continuously from the 24th of July 2014 to the 15th of January 2025. It made 3 trillion observations of 2 billion stars and other objects. It completely revolutionized stellar and galactic astrophysics. So we bid a fond farewell to the Gaia mission, which has stopped collecting data, but there are still many scientists working very hard to process all that data and get the best possible results out of that. There's other things we can measure as well. In this game, theoreticians are very clever people, and they can, if you give them some data, they can think of cunning ways to match it by varying the parameters of their model. So the more things you can measure, the more you can pin them down. One of the things that's important to know about a star is its metallicity, or its composition. This is an example of the type of data that you need to make an estimate of the composition of a star. This again is a spectrum. This is a very, very narrow section of spectrum at a green wavelength. This is very small, and I can see this is only 8 nanometers. So this is something like just a few percent of the visible wavelength range. Here you see this is the flux plotted as a function of wavelength for the 2 stars in the AIP eclipsing binary systems, AIP A at the top, AIP B at the bottom. And here are these Fraunhofer lines, these absorption lines caused by atoms absorbing the background, the radiation in the outer layers of the star. And the strength of these lines depends on the effective temperature, but it also depends on just how much of a given element there is in the star's atmosphere. So, for example, we can measure the abundances of scandium from this line on the left-hand side. And most of these lines will be iron lines. There's some calcium lines here and so on. So yeah, there's a dependency on the temperature, but we can make an estimate of the temperature from the analysis of the spectrum itself, or from the colors of the star, or directly in a few cases. And then this can be modeled using stellar model atmospheres and radiative transfer codes to estimate how much composition of the stars, essentially the metallicity, what fraction of the star's mass is made up of elements other than hydrogen or helium. Of course, there's a complication with binary stars, that when you point your spectrograph at the star, you get the light from both stars. But we have the techniques now, when you have multiple measurements, because the lines shift relative to each other, we have the techniques to pull the two spectra apart. This works particularly well for cases where you've got a total eclipse, because when you can make a measurement of the spectrum of just one star during the eclipse, and that gives you like a solid baseline to work from to then extract the spectrum of the other star from the combined spectra. But this is another thing we can measure. I think something to emphasize about metallicity measurements, these are model dependent, and they're actually quite sensitive to details of the analysis, which stellar model atmosphere you use, how you do the measurement of the depths of these lines, some of the assumptions you make about how the atmosphere of the star behaves. So it's difficult to get a homogeneous set of measurements for the composition of a star. Different analysts, different models, different techniques give slightly different results. Ideally, what you would like is to have like a uniform set of high quality spectra and analyze them all in the same way, using all the same techniques and the same models every time. So that if there's, say, a small difference between the metallicity measurements for two stars of 0.1 units, you know that's because one star is slightly metal poor compared to the other, and not because you use different techniques. But we're a long way from that at the moment. That's the type of information that we're wanting to build up. Okay, we have lots of measurements of the masses and radii of stars. My colleague John Southworth here at Keele has an online catalogue of them called DebCat. Here they are plotted as a function of the mass of the star against the orbital period on the right-hand side here. I've just plotted everything here. I've color-coded things red and blue. Immediately, one thing we can say is that not all these stars have any sort of estimate of their metallicity. So I've only plotted in full symbols the ones that have metallicity measurements. So that already cuts you down. For this particular project that I'm interested in, related to the planet host stars, we're interested in the mass range from about half a solar mass up to 1.5 solar masses. So we're sort of cutting down and cutting down. But the real problem with the existing database is that a lot of these measurements are based on ground-based measurements, where it was very hard before the era of things like Kepler and TET. It was very hard to even discover eclipsing binary stars with periods longer than a few days. And when you have a star that has an orbital period of a few days, which will be on the left-hand side of this left panel, what you find is that the orbital period of the star and the rotation period of the star are very close to each other. So most of the stars in the DebCat catalogue, most of the stars for which we already have good mass and radius measurements, they live in this little clump of stars down here on the at a value of P orb over P rot of 1, and with periods less than about 10 days. There's lots of these systems live around here. So what that means is, what's happened here is that tidal forces have forced the two stars to orbit in a circular orbit, and the two stars rotate at the orbital period. This is synchronous rotation. This is the same phenomenon that is why we only see one side of the moon, right? The tidal force of the Earth on the moon has locked its rotation period to be the same as its orbital period, so we only see one side of the moon. The same thing is happening here for these stars in binary systems. And the issue with that is we are trying to test models of normal stars, planet host stars. Planet host stars typically rotate with rotation periods of 10, 20, 30, 40 days. So it's really questionable whether a binary system which has an orbital period of, say, 3 days, which is very typical for these systems over here, on the right-hand side. If you have something with an orbital period of 3, 4, 5 days, that star would have been forced to rotate with a rotation period of 3, 4, 5 days for maybe billions of years. And that's, you've got to question whether that's a good way, a good exemplar, a good template or benchmark for a planet host star, which might be rotating 10 times slower. A lot of the uncertainties in stellar models are to do with the way that material moves within the star, the sort of mixing and diffusion of stars. And rapid rotation, we know, does have a big impact on the way that elements settle and move within a star. So what we would like to do is move to orbital period, longer orbital periods, sort of above 10, 12 days, and have a metallicity measurement. And when you do that, when you sort of start cutting this sample down, you see that you're sort of down to maybe, a dozen, 20 systems that are suitable for calibrating models of planet host stars, at least to the sort of precision that we need nowadays. And again, I'll mention that the masses and radii here are all good. They're all, accurate to 2%, but the temperature estimates and the metallicity estimates all come from distant sources, so they're very inhomogeneous. So there's definitely work to be done increasing the number of systems in this green box and getting a more homogeneous set of measurements for temperature, luminosity, and metallicity, ideally tied down to direct measurements using those techniques I discussed earlier. Why do we need to test stellar models? We need to test them because different models make different predictions. There are lots of uncertainties in stellar models. Even things like atomic data. Atomic data, by that I mean, how do the atoms interact with light? A star is a balance between the energy flowing out from the center, mostly in the form of gamma ray radiation and high energy radiation in the interior of the star, and that photon pressure balances the star against gravity. And so the way that light interacts with matter at high densities and high temperatures it's essential to understand that to get the right structure model for a star. That's very hard to measure. It can be computed, but computations always have some uncertainty. There are issues to do with the composition of the star. We can measure the surface abundance, but that doesn't necessarily reflect the interior abundance. There's been a long-standing problem in stellar astrophysics for decades now, that if you take the best available models for the modeling the atmosphere of the sun and apply them and measure the composition that you get measured from the light we see emitted from the sun does not give a good match to the interior structure of the sun measured from helioseismology, a technique that I'll discuss in a little while. There's this sort of real tension between the two most fundamental ways we have of sort of studying the sun's composition. And there seems to be no easy solution to that. There's definitely something going on we don't understand. Helium abundance, you can't measure the helium abundance directly for solar type stars. We only have really sort of indirect estimates for how much helium a particular star has. It's very hard to estimate that number. For the sun, we know it's around 28%, but how that varies from star to star, how it correlates with other properties, really uncertain. I've mentioned already these sort of mixing processes, the fact that the heavier elements tend to sink towards the core. Some elements are sort of sensitive to the radiation field and actually tend to float to the surface, rotation impacts and all that. And these solar type stars, the outer layers of solar type stars are convective. They're very, very turbulent. It's like a sort of intense boiling type motion, but models of convection are incredibly difficult to produce that are realistic and very expensive in computer time. And if you want to calculate lots of stellar models, you need a simpler prescription of convection, and that how you try to capture the effect of convection in a star. Huge sources of uncertainty. You can sort of see that happening in this graph that I've taken on the right-hand side from a very nice paper by Jamie Tayar et al., A Guide to Realistic Uncertainties in Estimating Properties of Solar Type Stars. So we have a luminosity temperature graph here, the Hertzsprung-Russell diagram. The black dot here is where the sun is. The lines here are where the sun is predicted to be using different grids of stellar models. The point here is the point along this evolution track. So say, for example, this purple line, the star would have formed off the bottom of this graph, and then as it ages, as it burns, as hydrogen is fused to helium in the star's core, the models predict that it will move upwards and leftwards in this point, and it's predicted to be at this purple point at the age of the sun. You can see that these models differ in their predictions. Now, you can say that the DSEP and the GASTEP models are clearly better than the YREC and MIST models. The people who produce those models are perfectly aware of the fact that their models don't match well the properties of the sun, but these models would have been tuned to match the properties of other stars. But what they can't seem to do, because of all these uncertainties, is match both the properties of the sun and the properties of other stars in the galaxy. There's a summary of this, which is actually, I'll give a quote here from the author of these MIST models, is that the more you know about stellar models, like sausages, they cease to inspire respect in proportion to, as you know, how they are made. The more you look into the details of what goes into a stellar model, the more you realize that there are real uncertainties in there. This is not because the people who generate these models are some of the cleverest people I know, but it's really hard to figure out what's going on inside a massive ball of magnetized, rotating, convective, fusing plasma. It's a tough physics problem. Okay, so we're going in three parts. I think I feel like I should do a little summary as we go along. Modern instrumentation, survey data, and analysis techniques, we can measure mass, radius, and luminosity of normal stars and detached eclipsing binary stars, an order of magnitude more precisely than was possible 20 years ago. We're now working at the sort of 0.1% level, 0.2% level for masses and radii, the 1% level for effective temperatures. And we need this high quality data so that we, particularly for long period binaries where the stars are well separated and look like normal stars, to calibrate all that uncertain physics in stellar models. Okay, let's move on to the PLATO mission. So the headline here, the aim of the mission, one of the aims of the mission, perhaps the main aim of the mission, is the detection of terrestrial exoplanets in the habitable zone of solar-type stars and characterization of their bulk properties needed to determine their habitability. So we're looking here at trying to find a mission that's able to detect Earth-like planets around bright stars, where we can not only just say it's there, but actually make some measurements of that Earth-like planet's properties. This is a picture of one of the engineering models that's being used to develop the mission. The real spacecraft is being built now. I believe they're about halfway through putting the cameras onto the bench, onto the optical bench for the real mission. Just to give you an idea of the scale here, this is a big thing, right? This is maybe what, 10 feet, 12 feet high. When the solar panels extend, it's a big old spacecraft. The launch is scheduled for December 2026, and it was recently announced that is going to be on the new Ariane rocket. So the idea here in the way that the planets will be detected is the transit method. I'm sure this will be familiar to some of you, to many of you. On the left-hand side, you have a picture of a sun-like star, and there's a planet orbiting around it. And as the planet orbits around the star, from the viewpoint of the Earth, its orbital axis is arranged so that the planet blocks some of the light. And so there's a dip in brightness. And that's what you're looking for. This is the transit technique. It all looks very simple here because you have a nice model going along, and it all looks very easy. But if you think about trying to do this for the detection of an Earth-like planet orbiting a sun-like star, then you end up with data like the simulated data on the right-hand side here. So I've simulated an Earth-Sun transit signal, including some estimate of the stellar noise. So the dominance, there are two sources of noise here. There's a reason why these individual faint blue points, so these individual faint blue points are a measurement made every 25 seconds of the brightness of the star. And they jiggle around. Partly that's just because of the faintness of the random arrival of photons from the star, that sort of photon counting shock noise type effect. But there's also stellar noise. The fact that the reason I like the simulation on the left-hand side, this particular movie, is because it has a sort of realistic looking sun here. And you can see that there are sort of dark areas and bright areas and spots, and there's all that convection and turbulence. We'll see later that there's variability on all sorts of timescales. So the model on the right-hand side has some of that stellar variability built into it, so, under certain assumptions. I've stacked together here 4 transits, assuming that you observe 4 transits. And then the dark blue points is what happened if you take an average in sort of, what are they? I think they're like in 10-minute bins, you can take the average. And you can see it's only just about detectable. This signal is only 80 parts per million. This is what the PLATO mission is designed to look for. This was something that was achieved by Kepler in terms of its precision, but Kepler really struggled to find Earth-like planets orbiting sun-like stars because of the amount of stellar activity. The amount of stellar noise was larger than expected. So that's been built into the design of the PLATO mission to account for that. The 24 cameras of the PLATO mission have a sort of rather odd configuration, and the way that they point, you can see on the left here, they don't all point in the same direction. So the fields of the groups together in groups of 6 cameras, and each group points in a slightly different direction. So you get this sort of the observations in the center of the field of view. You do get 24 cameras, but there's regions of the sky that the PLATO will observe where you only have, say, 12 cameras or 6 cameras. So we're sort of hedging our bets here. It's not obvious whether it's better to just point all the cameras in the same direction and observe everything with 24 cameras, or you could spread them out and increase the number of stars that you want to observe. So here we sort of hedged our bets and done a bit of both. So there are 26 cameras, so a total of 81 with 81 megapixels per camera, and the field of view is 1037 degrees squared. So that means that PLATO can observe 200,000 stars in one go. That's actually limited by the bandwidth, just downloading the data. So the left-hand side here is the first field that will be observed. It's in the southern hemisphere. It's more or less centered on the star Canopus. It includes the Large Magellanic Cloud. And this field will be observed for 2 years at least. Once the mission is launched and the instrument performance is understood, we'll then make a decision about whether to stay with this field for maybe 3 or 4 years, or whether or basically they will then make a decision about how long they will stay on this field. It'll be at least 2 years, and how long, and then after that they'll move to a northern field. The right-hand side here shows the PLATO field of view on the whole sky. This is the whole sky image. So there's the southern field that will be observed first for at least 2 years on the right, bottom right here. And there's the northern PLATO field in the top left. The pink square here is the Kepler field of view. You can see that the PLATO field of view is much larger. And there may be a step and stair phase. It may do like an all-sky survey, or it may not. That's yet to be determined. There is a huge amount of work going on to get ready for the PLATO mission. There are literally hundreds of scientists involved. One area of the PLATO mission that I'm involved in is the PLATO stellar analysis system. If you want to make accurate measurements of a planet property, this requires accurate estimates of the host star properties. The aim of the PLATO mission, the requirements of the PLATO mission are that you should be able to measure the radius of the planet with an accuracy of 3% and estimate its age to an accuracy of 10%. That's really hard. In fact, it's not possible currently to estimate the age of this star accurately to 10%. We do need to improve the stellar models before we can achieve that. So there's a huge ongoing effort to develop processes to provide the best stellar possible property estimates to make estimates of the mass, radius, density, luminosity, age of stars. There are ongoing observing campaigns. There are new stellar models being developed with the latest physics in them. There are advanced analysis techniques being developed, all huge amounts of work. I've just pulled one flowchart out of one technical document that I have access to. This is like a 31-page document, just to sort of give an idea of the complexity, the number of data sources that are being used, the number of sort of software modules that are being written. All this needs to be tested, all this needs to be calibrated. Essentially, what we need are benchmark stars that we can apply these techniques to, and essentially check that this huge amount of software that's being developed in these new analysis techniques to make sure that they're working, to calibrate them, to work out the bugs, to reduce the uncertainties. So this is why we have a need within the PLATO mission for these benchmark stars, these stars where we have independent measurements of the star's properties. And that's the area of the PLATO project for which I have responsibility, to develop these PLATO benchmark stars. Yeah, I mentioned helioseismology. Let's explain helioseismology, and that will take us on to astroseismology, which is one of the techniques that will be used by the PLATO mission. Just to give you a feel for what we're dealing with here, on the left-hand side, we have what's called a power spectrum. So I'm going to click on this, and you'll hear a note. This is actually a recording of a bassoon playing a particular note. I hope you can hear this. There you go. That sound, you can process it and measure the frequencies that are present, the notes that are present within that sound. And that's what the blue line in this graph is. So this is being plotted from around about 100 hertz, which is at the bottom of the human audible range, up to about 2000 hertz. So this is quite a wide range of frequencies. The power here is plotted on a logarithmic scale, meaning that a change of, I know this is plotted in decibels, which is slightly awkward. 10 units on this right-hand side corresponds to a change by a factor of 10 in the power. So this main peak here is several times stronger in terms of the amount of energy at that frequency compared to the other peaks. If you plotted everything here on just like power rather than logarithmic power, you wouldn't see the details here. But you can see with musical instruments, they have a particular timbre because of the amount of power in the different harmonics. And that's something that your brain can hear and interpret and work out what it's listening to. You can do the same thing with the sun, surprisingly. We can't hear the sun, but what we can do, we can see sound waves within the sun. As the sound waves in the sun hit the surface, they make the different areas of the sun's surface brighter or fainter, and they also move the surface slightly. So you can see it also in the way that the surface moves from its Doppler shift. So this is a power spectrum observed by the Birmingham Solar Oscillations Network, a network of 6 instruments around the world that measure the motion of the sun's surface as though it were a distant star. And you can turn this into a sound as well. So if I click on this, you can hear it, and I'll tell you it's not as harmonious as a bassoon. Okay, now this has already been filtered to take out a lot of low frequency noise. The sun varies on all sorts of timescales. But if you listen to it, there is a sort of characteristic note to it in there somewhere. There's a lot of detail here. This is a very narrow range of frequencies, but you can see there's a lot of structure in here. And all this structure is related to the interior structure of the sun. This gives you a way to probe the stellar interior. Incredibly powerful technique. I just hit the wrong button. Okay. We can apply that technique to more distant stars as well by measuring how they vary in brightness. These brightness measurements are incredibly subtle, but it has been measured. The Kepler mission did this very effectively for large numbers of stars. Without getting too much into the detail here, the bottom purple here is the power spectrum of the sun. This is not filtered, so you see the sort of overall fact that there's a lot of sort of rumbling noise at the lower frequencies, but you see this sort of collection of structure at a characteristic frequency that's characteristic of the density of the star. Different stars oscillate at different frequencies. There's a lot of detail in here that you can use to pull out the interior structure of the star. And you can use this, and the PLATO mission will use this method to estimate the properties of the star that it's looking at, the planet host stars. In particular, the details of the frequencies at which a star oscillates, if you can combine that with stellar models to estimate the age of the star. So for the brighter stars that are observed by the PLATO mission, the brightness will be measured to such high precision in order to detect the Earth-like transit that the astroseismology sort of comes for free, and that detailed analysis can give us the mass radius and age estimates of the star. So that's going to be an important aspect of the mission. Now, because astroseismology is such a sensitive technique, it's a really good way to sort of, if a stellar model can match those frequencies, it must be doing pretty well. If you combine that way of testing stellar models with independent estimates of the mass and radius that you can get with eclipsing binary stars, you can really pull out some very sensitive details of the model. This has only really been done using Kepler data for giant stars. Giant stars have a much bigger astroseismic signal, and there are some oscillating eclipsing binary stars where you can combine the analysis of the oscillation frequencies with a good prior knowledge of the mass and radius of the star. This top panel shows the type of thing that you can measure with that. This number alpha MLT is effectively a measure of how efficiently convection moves energy through the star. And there's a there's a measurable relationship between the composition of the star. This M over H is the metallicity on some sort of logarithmic scale. It appears that from the binary stars, at least, that the efficiency of convection is larger in stars that are more metal rich than the sun. This can be seen just using astroseismology, but it actually turns out that the slope of these relations is different between the eclipsing binary stars and the measurements that you infer just using astroseismology from a large number of red giants. That's because there's other things going on apart from metallicity that are impacting on the efficiency of convection. So disentangling all these effects becomes very important. Combining astroseismology and eclipsing binary star analysis is an incredibly powerful way of pulling out these fine details of the model. We can do it currently for giants. There's only one set of dwarf stars, sun-like stars, for which we can currently do that. The oscillations of the stars Alpha Centaurus A and B, the third brightest star in the sky, Alpha Cen, is a close binary system composed of a sun-like star and a lower mass star. Because this is the closest star system to the Earth, along with Proxima Cen, the closest star to the Earth. It has an orbital period of 70 years. The orbital period has been measured from literally just measuring the positions of the two stars relative to each other on the sky. We have their radial velocities. This is a different way of measuring masses and radii for stars when you can actually have a visual double where you can actually see the two stars orbiting each other when they're very close. And we have direct radius measurements because long baseline interferometry has actually resolved the apparent disks of these stars on the sky. So we have very good quality data for this particular pair of sun-like stars. The graph on the left is one paper that's analyzed the combination of the mass, radius, and luminosity of the stars together with the astroseismology. The green and blue points are again, this convective efficiency is a function of the age. Different stellar models here, or the green and blue stellar models, are the ones that match the mass, radius, and luminosity of the two stars at a given age. But then when you add in the frequency of oscillations, the astroseismology, you then get these triangles. There are different assumptions made in these different models. But you can see that we're starting to get information when you combine mass, radius, luminosity, and astroseismology. You can get information about how efficient convection is in these stars relative to the sun. So Alpha Cen B, even though it's sorry, I've got that on my around. Yeah, Alpha Cen A, which is the sun-like star, is very similar to the sun, but it has less effect. The convection is less efficient. This is nice. But this is just one example. We would like measurements like this for dozens of stars, so we can understand why is it that different stars have different convective efficiencies. So, summary of part 2: the PLATO mission will revolutionize our understanding of planetary systems and stellar astrophysics, and those things are sort of related, combined to each other. Benchmark stars are needed to calibrate the data analysis techniques, validate the quality of the science results. In the development phase, while we're still waiting for PLATO data to arrive, benchmark stars anywhere on the sky are useful to make sure that we're able to characterize the stars in the PLATO field accurately. But what we're really looking forward to during the operations phase is benchmark stars that will be observed by PLATO, where we can do end-to-end tests to compare the properties of the stars that we've measured independently to what is coming out of the PLATO machinery. And also, the holy grail for us is some solar-type stars where we can see the astroseismology in the PLATO data, and we have independent mass, radius, and luminosity measurements, so that we can really start to understand how solar-like stars behave. Let's move on to then how this PLATO mission and eclipsing binary stars, why some sort of professional amateur collaboration arises from that. I have to say I don't like the word amateur for observers because it has a sort of hint of amateurish about it. And in my experience of working with citizen scientists, the results are nothing but certainly not amateurish. Okay, let's get to the point. CPD minus 54810. This is one of the stars for which we have direct luminosity effective temperature measurements done by my student Nikki Miller. The top right panel here are the test data, which are of incredible quality, and so we also have good spectroscopy for this system. So again, we have these masses and radii measured at the sort of 0.1% or even better level. So we have very, very solid mass and radius estimates for this. But if we only have the test light curve, we only have one measurement of the relative flux contributions between the two stars. TESS observes in the sort of far red near infrared band. But what we would like to do is know how much light are the two stars producing across a range of wavelengths. The way to do that would be to observe this total secondary eclipse and measure the flux ratio between the two stars at a variety of wavelengths. Those observations are not easy to schedule because these eclipses happen, roughly once every 4 weeks, every 26 days. And this is quite a bright star. So professional, big telescopes have small fields of view. And so in a small field of view, if you put a sort of 10th, 11th magnitude star in the middle of the field, there's probably nothing of its similar brightness nearby to compare for calibration purposes as a comparison star. A colleague of mine suggested I get in contact with TG Tan, who is a citizen scientist. He has a 12-inch telescope. He lives in Perth, Australia, and he's able to get good quality photometry. So TG observed this star for us. He got some beautiful measurements in the BVR and I bands from the blue to the near infrared. And this is perfect. That covers most of the flux that's emitted by the two stars, and it gives us a really good measurement of the flux ratio between the two stars. And so because of these measurements by TG, who was a co-author on the paper, combined with the analysis that we've done already and the Gaia data, we were able to sort of get below this 50 Kelvin precision in the effective temperature measurements. So this was I really enjoyed doing this. I enjoyed working with TG, and I thought it was really nice that a citizen scientist can have a real impact on these sorts of fundamental measurements. I've been thinking a lot about what type of stars we want to observe for calibrating observing techniques in particular, but sort of end-to-end tests. A lot of the measurements that are going to be made for the planet host stars in PLATO, or the stars that PLATO will observe, a lot of these will be done on a sort of industrial scale using instruments that observe hundreds of stars or thousands of stars at a time using fiber-fed spectrographs, and then they have the whole sort of machinery set up to process those spectra and automatically produce estimates of temperature, metallicity, and so on. So for an end-to-end test, you don't really want to have to do some sort of special treatment as you normally have to do for a binary star, because there's light from two stars. And the machinery for these surveys is mostly set up to analyze single stars. So you can sort of compromise here a bit. What you can do is try and find systems like the one shown on the right here, HD22064, where the companion star is a faint red M-dwarf star that contributes maybe 1% of the light at the optical band. Because at that level, when the companion's only producing about 1% of the flux, it doesn't really have an important effect on the measurements that are made at optical wavelengths. So there might be a small correction that you would need, but you don't need to be very accurate in that correction. It's a small correction. You can essentially, if you pick these stars where the optical flux ratio is about 1%, you can do these end-to-end tests. You can make a measurement of the masses and radii of the stars. We have the instrumentation nowadays to pick up those faint companions and measure their orbital speeds and do the whole sort of mass radius measurement thing. We have those techniques then for measuring the effective temperatures of the star. So we know the temperature, mass, and radius of the sun-like star in these systems, and the impact of the low mass M dwarf is pretty small. So we're looking, what we want then is these eclipsing binaries, which are bright, so that we can do the follow-up observations without too much expense in terms of telescope time. Ideally, it's nice to have total eclipses because it's very unambiguous then how much flux is coming from each star. We want this thing that the orbital period is long. We can go a little bit shorter than 10 days here because the companion is low mass. It doesn't have such a big impact on the primary sun-like star. So maybe 8 or so days or longer, ideally longer. Of course, they get harder to find at longer orbital periods and they're rarer, but still, that's what we would like. Yeah, we aim for an optical flux ratio of about 1%, and we're looking for these sort of mid-F to late G type primary stars, which are the sort of type of stars that are being targeted by PLATO in its for its prime mission of detecting Earth-like planets orbiting sun-like stars. What would be a real bonus, and we would definitely like some of these stars to be in the PLATO long stare fields. Those are obviously higher priority stars, because then we have the opportunity to combine the analysis of the binary star with astroseismology once PLATO gets going. So this is an ongoing project. HD 22064 is in a collection of benchmark stars that I identified using test data. 22064 was a bit of a bonus because I just discovered it had been observed already by an infrared spectrograph a few times, and I was actually able to do the mass radius and luminosity measurements. For the other stars in the system, we need to go away and get the measurements to the spectroscopy that's needed to measure the masses and radii, and that's an ongoing observing program with the HARPS spectrograph and the NERPS spectrograph, which observe in parallel on the ESO 3.6 meter. The HARPS spectrograph is a spectrograph that's been used for lots of planet hunting over the last 2 decades or so, and in the last few years, ESO added a parallel channel to the instrument, which can observe in the near infrared. In the near infrared, the companion star, the M dwarf, which is cooler than the sunlight star, it produces more of its flux in the infrared. And so you have that sort of advantage that you can pick up the companion in the near infrared, measure its orbital velocity, get the masses, get the radii, and so on. So this is where citizen scientist observations come in. As we saw, it really helps if you have measurements at more than one wavelength of the flux ratio. Those are difficult to schedule, particularly for long period systems. And so I've started a sort of pilot project with various observers within the AAVSO and other people who I know. This is one example of some data obtained by Andrei Kovacs for one of the target stars that I identified, Tycho 854722-1. It's 10th magnitude star. This is one of the shorter period systems. We're down at 4.24 days here. Slightly shorter period than I would like, but it's actually quite a nice system. We should start somewhere with some of the slightly easier systems. What amazes me is that these data are actually taken just with a 7-inch telescope. I think this is probably at the limit of how small a telescope can be to make useful measurements of this type. I think the advantage that this telescope has, even though the aperture is not so great, it appears to be some sort of astrograph with a short focal ratio. So it's got a big field of view, so lots of comparison stars, good quality CCD. These are observations in the V band with a 58-second exposure, and it's a good site. And so there's in the data here are on the right-hand side. There's something a bit funny going on at the start of the observations. Maybe that was a high mass. Maybe we'll be able to do something to correct for that. It's the stability of the measurements is really the challenge here. With these eclipses, it takes several hours. Trying to keep a uniform calibration of the data is tough. But still, there's a definite detection of a secondary eclipse there. Andrei actually observed the primary eclipse for this system as well. And I've done an analysis. I excluded this data that needs further investigation. But there's a definite secondary eclipse in there. It's not detected at high significance, but I have that V-band flux ratio, even though it's a marginal detection in terms of measuring exactly how deep it is. The point is that's limiting how much flux is coming out in the V-band from the M dwarf. That precision on that, it's the error bar that I'm interested in here. Whether this number had turned out to be 0.1 or 0.5, whatever it is, it's this sort of accuracy of working at the sort of better than 0.5% in terms of the flux ratio measurement precision that we need. That's helping to get, they'll help us to get a more precise estimate for the effective temperature of the 2 stars. The primary eclipse observations are also useful to make sure that there's nothing funny going on. The radii of the star should not depend on let's get this right. The radius that you infer for the star, what measurement of the radius that you make, that shouldn't depend on the wavelength. So if there's a 3rd star in the system, if there's something weird going on with maybe star spots or something like that, you would see that with effectively the radius that you measure at different wavelengths. If that varies, if there's that would be indicative that there's something going on that needs further investigation. So these measurements of the primary eclipse, which is obviously much easier to see, this is about 15% deep. Those are useful as well to make sure that we understand the system, we've characterized it accurately. Okay, so this all sounds very nice. We have a pilot project going. We have a plan. We have a well-identified need. Now all we need is somebody to do the work. And this is where we have some breaking news. I got an email yesterday that I have been recommended for funding. So I will be advertising for a research assistant this summer. I have some of my time paid for to work on this. The panel agreed that this was worth doing, and even though the funding landscape in the UK is not good at the moment, I've managed to secure some funding for this project. So we're going to be moving from the pilot projects and thinking about things and knocking out the occasional paper to actually designing a proper observing program to obtain the new high quality measurements that we need, these fundamental properties of benchmark stars. We've made a start, but now that we have the funding, we can employ a researcher and I can spend more time working on it. I've not wanted to collect too much data from citizen scientists, or in fact from anybody, while I've been uncertain about whether or not I can actually get it published. But now that I've got some funding, I'm sort of happy to go ahead and start planning observations that would improve the quality of the results I'm going to get, and enable citizen scientists to contribute to that. And I think this could be a really nice way for citizen scientists to get involved in the PLATO mission, to showcase what you guys can do. I've seen some very impressive results from the ASVSO, AAVSO, and other citizen scientist projects. I think it would be a really nice showcase for the AAVSO to show what they're capable of and make a case to the PLATO ground-based observing program. The PLATO mission is very unusual in the European Space Agency in actually having a ground-based observing program that will do the follow-up as part of the mission. Obviously, if you're trying to detect an Earth-like planet, that's, you're sort of restricted to using the biggest telescopes in the world. But there's going to be all sorts of stuff that gets discovered by the PLATO mission. There's going to be all sorts of planets. Some of those will have eclipses and transits that can be observed from the ground. The observations from the ground can be very useful to distinguish what's going on, to distinguish false positive detections from real detections, to work out which of these faint blips really need to be observed with large telescopes. So I'm very positive about the future, and I'm hoping to design an observing program and get that out to the AAVSO with a request for observations over the next few months. And I'll stop there for today. Thank you very much.
Dr. Maxted, thank you very much for this wonderful presentation. I believe PLATO is probably one of the most interesting upcoming spacecraft, and given that its magnitudes are pretty well, its magnitude limitations pretty much overlap with what amateur astronomers are capable of observing, I think it's actually a very excellent way that amateurs could get involved. So I would just ask if anybody has any questions, if you could please use the Q&A box at the bottom of your screen to submit those. We have about 16 questions in the queue right now, but we'll try to answer as many of those as we can. But while folks are submitting their questions, I'm going to abuse my privileges as host and ask you a question about spectroscopy. So the AVSO, as you know, is best known for doing photometry, but we also do stellar spectroscopy, exoplanet photometry, and sunspot counting. We do have a few members that have relatively high resolution spectrometers. So we're talking, well, for like amateur equipment, an R of 30,000 is about as high as what it goes. And a few of them actually have shell spectrometers mounted to 1 meter telescopes. They're usually fiber fed, temperature stabilized things. There's a handful of those within the organization. Would spectroscopic data from an instrument like that be of any use to your program, or do you really need that like meter per second calibrated stuff for the your work characterizing these stars?
With a 1 meter class telescope and a resolution of 30,000, I think you can do useful work. I think it does require that you throw quite a bit of time at it, but the signals are quite large. The oscillation amplitude, the orbital velocities are large for binary stars.
Yeah.
And what you can do, with a 4 meter class telescope or an 8 meter class telescope, I can sort of do the whole orbit in a week and get the masses pinned down. But what I can't do is monitor the long-term behavior of the binary system. The thing I always worry about with binary systems is, okay, I'm treating this like 2 stars orbiting each other. Is there something else going on? Is there a third star in the system that's somehow affecting my measurements? And it's really nice to have a good understanding of if there's something else going on in the system. Is there a third star? So if you're prepared to put in a long-term observing program and monitor these things over years, What you can do with the radial velocities is monitor them for long-term drifts in the radial velocity that might tell you about the presence of a third star in the system that you would need to account for. So yes, you can do useful work with it. It does require that you are in for the long haul.
Yeah, and I did notice that like the Gaia spacecraft had a medium resolution spectrometer of an R of about 10,000 or so, and
Yeah.
they released a very nice binary star catalog along with Gaia DR3. So it should be relatively easy for AVSO and you to pick out some stars that might be observable with various ground-based instruments as well. So we'll go ahead and switch over to the QA here. And so early on during your talk, you were discussing your eclipsing binary models, and Enrique is curious if those models are somehow impacted by metallicity.
I want to just say no. It's a bit more subtle than that. The limb darkening effect that I mentioned, that curvature at the bottom of the transit. So that's an effect called limb darkening, which the extent to which the edges of the disk of a star are fainter than the central regions do depend on the composition of the material, but mostly it just depends on temperature. The correction for metallicity is pretty small. And we understand that well because we have all this high quality data for transiting exoplanets, in fact, transiting hot Jupiters, particularly from Kepler, also from TESS and the KEOPS mission. That's something I've been working on. Limb darkening is one of those things that almost nobody cares about it because it's just this annoying thing. You just like, it's just a number you have to put in your model. And so I put quite a lot of work into actually understanding that number and how accurate the models are. And it turns out the models are actually very good. And so we understand that effect. So there is a very small dependence on metallicity, and we understand it. Just a very slight tangent here. It turned out that people are going to care about limb darkening a bit more because it turns out that most of the models that you use to model limb darkening, they're very good, but they're not quite right. And the reason why they're not quite right, when you have very high quality data, you can see they're not quite right. And that little offset is because those models don't include magnetic fields. So some of my colleagues got some more advanced models, more expensive models that do include magnetic fields, and you can explain that little offset. So, and then you can reverse that argument. If we're going to make very, very high precision measurements of the light curves of transiting exoplanets with PLATO, we can adjust the magnetic field in the model until it matches the limb darkening. So it turns out by being virtuous and worrying about the details of how we model binary stars, it turns out we've developed a new method for measuring magnetic fields in stars.
Oh, that's wonderful. Yeah, I was also curious about the effect of limb darkening because I noticed that you had optical interferometric data mixed into your pipeline. So, are you going to pull in some data from, say, the VLTI or Chara or some other instruments?
That's planned for cases where the stars are near enough. That's going to be the very brightest stars in the PLATO field. So that's a quite limited applicability, at least for the solar type stars. So it turns out actually that there's not that many stars in the PLATO field where angular diameters for interferometry will be available, but where they're available, we'll use them.
Oh, that's great. Another question here was that a couple people were curious about how you account for any kind of circumstellar material that might be causing, say, like an infrared excess in your models.
By avoiding it. We systems where there's no mass transfer between the stars. And so as far as we can tell, these will be very quiet systems. We do have some information about the circumstellar material. What we can do is look for absorption lines that don't move when the two binary stars are moving. In fact, there's a particular line we use due to sodium that we use for estimating the amount of atomic gas between us and the star, because that seems to be quite tightly correlated with the amount of dust. One of the things you have to correct for when you're making these temperature measurements is how much of the flux is absorbed by dust between the star and the Earth. For most of these systems, that's a very small correction, but we make that correction nevertheless, using this correlation between the amount of sodium absorption and the dust extinction. And when we look at that line, we tend to just see one line that's at a different radial velocity to the binary center of mass velocity, meaning there's no evidence for any other gas floating around the system.
Okay. Yeah, no, that's a good way to avoid that kind of a problem. It causes a lot of mess. Gary here was wondering, in certain circumstances, you're probably going to run into to systems that are eccentric, and he was curious if there's any advantageous aspect of going for systems that are purely circular, or if the more eccentric systems offer some additional data.
As you go to longer orbital periods, you do tend to find that the systems become eccentric. That's not a problem. The calculations are a little bit more complicated, but we've had the equations and methods to do that for decades. You have good constraints on the eccentricity, both from the light curve. The eccentricity affects where the secondary eclipse happens, and also how wide the two eclipses are. So we actually get independent measurements of the eccentricity from a detailed analysis of the light curve. And we also get detailed information about the eccentricity just from the shape of the radial velocity curve, how the radial velocities vary with time. And those are independent. So in a way, it's a quite nice check that you're doing a good job, that you get the same eccentricity and also the same information about the orientation of that long axis of the eccentric orbits relative to the observer. You get two independent measurements. So it's a nice cross-check that you're doing things accurately. And I like eccentric systems just from the point of view that if the system's eccentric, to have maintained its eccentricity, there can't be strong tidal forces. And so I like that as a way of sort of justifying that these are good templates for normal stars, because there's clearly not a strong interaction between the two stars if they're still able to maintain an eccentric orbit.
Yeah, it's good. So on Andrei Kovacs, whose data that you featured in there, he made a note in the question box here. He indicated that he'd like to highlight the data that he submitted to you was actually acquired using one of AVSO's resources, AVSONet. That was one of our 7-inch astrograph, the Takahashi instruments that you mentioned. So, for those of you that are interested in participating and helping out Pierre do research, if you're an AVSO member, just please keep in mind that you'll actually have access to additional resources just as being a member of the organization. We had a couple other questions here. So like Michael Poxon, for example, he is our Young Stellar Object section leader. He was curious if any of the algorithms that you showed could actually be used to deconstruct variations that you see in pre-main sequence stars. So things that might be caused by variations in circumstellar disks or rings or things like that.
So what we tend to do for eclipsing binary stars is, because we're targeting systems that are simple, they can be modeled as spheres, or they can be modeled at least as ellipsoids. That enables, if you simplify the model, that enables you to do the calculations very fast. And the advantage of that is that you can explore a lot of models very quickly and really check that your uncertainties are accurate, that you've really explored all the possibilities effectively by doing things really fast. What the disadvantage of that is that you can't use those models to study things like accretion disks. You can maybe adapt them to do a small amount of surface activity like star spots. The code that I wrote, the LC, does have the option to put spots on the stars. But no, we tend to use models that are sort of specialized and have are very fast, because they're very simplified. There is an alternative approach, which is to use a binary star model where you can add in as much complexity as you want. A good example of that is the one developed by Andrei Koshar at Villanova, which is the Phoebe model, Phoebe, if you want to look it up. And when that was being developed, I remember that they were very proud of the fact that if they wanted to, they could model the eclipses of a UFO by a Ferrari. I mean, they can do anything. You can put any sort of shapes in there you want. You then have to sort of grid that up. You have to do the numerical. If you want to do things very precisely, you have to have a very fine grid, so it can be slower. So that's the disadvantage. Although Andrei has been working recently, I'm really looking forward to seeing the results of this. Machine learning techniques are now available, where what you can do is build a training set of models, which are as complex as you like, and you train up some sort of neural network to predict the light curves that you get for different assumptions and different parameters. And the speed up is amazing. So that disadvantage of having a complex model that, if you compute it in detail, is slow, you can work around that by training up a neural network to do it really, really fast. So I think that's actually going to be the future, is to actually have quite sophisticated models, build a large training set, and then you can do things super fast with a neural network.
Yeah, we've been thinking about starting up a choice course that would be related to using Phoebe for binary star modeling. It is really an incredible tool, and it's open source, so people can just go out and grab it. So, you know, it's really opened up a lot of interesting opportunities for citizen scientists to enter that next level of detail towards creating models.
Yep.
Roll here was curious. From what I recall, Plato has about 8 fast telescopes that are kind of magnitude limited between fourth and eighth magnitude. And then they have 24 of these normal cameras that I believe are limited between eighth and 16th magnitude. Roll was wondering how many stars out of say like your first field that you're going to be observing, do you think will actually be observable with by citizen scientists in addition to Plato?
Okay, so the 24 cameras will all observe bright stars down to about 10th or 11th magnitude. There are going to be about 5,000 stars in the selected field that are between around about 4th magnitude and 11th magnitude, and that are solar type. The algorithms to enable precise measurements of the brightest stars in the field are being developed. Even though they're saturated on the detectors, it turns out there are ways to still measure the bright stars. So all the bright stars, 5,000 stars between something like about 4th and 10th or 11th in that field will be observed by the normal cameras. There are also 2 fast cameras that are used for guiding, and those can run at, if I remember, it's either 2.5 or 5-second cadence. That takes a lot of bandwidth. So there'll only be, I think it's something like 300 stars will be observed by the fast cameras. They just observe the central region of the field, and they'll observe in a very broad blue and red band.
Okay. Yeah. Next up
I think
here. Oh, yeah.
There's also there's what's called the P5 sample. So there's also the M dwarfs and the fainter stars. So there's also stuff between 11th and 13th where you don't get such high quality measurements because it will do the processing on board rather than downloading a little postage stamp image. But there are a lot of those. I can't remember the number, but it's like tens of thousands. And there's also 8% of the bandwidth is available for guest observers to look at whatever they want.
Oh, that'll be really interesting.
Yeah, that's for complementary science. Yeah.
Yeah. Jonathan was curious if you could describe a little bit about the differences between, say, the Plato mission and the TESS mission. I remember like TESS has relatively large pixels compared with Plato.
I think the pixel size is actually comparable. The difference is the number of cameras and the aperture of the cameras. And so it's essentially in the TESS can deliver high quality photometry, but it's not high quality enough to detect the transit of an Earth-like planet around a sun-like star. It also has the cameras are sort of more spread out, and so it observes, if I remember right, it has a field of view. Each camera has a field of view of 24 degrees, and they sort of stack them in a strip. So it's an all-sky survey. So TESS is scanning the whole sky. It was designed essentially to find planet systems that were good for follow-up by James Webb Space Telescope. So it's looking for bright planet systems with relatively deep transits, short period systems where you get frequent transits. It doesn't stare at one field. There are regions of the sky where you get continuous observations, but essentially it's in the because of the aperture of the number of cameras and the aperture of the cameras, TESS doesn't deliver the photometric precision, the very stable and very highly precise measurements of the brightness that you need to get down to the measurement of an Earth-like planet around a sun-like star. But it produces beautiful data for bright stars of a quality that's for eclipsing binary stars. It's well amazing, as you've seen.
Yeah, they're absolutely wonderful. So just so you're aware, I've been seeing several messages in both the chat and also in the Q&A box here about people that were indicating they're more than willing to help out, and so that brings up a kind of a separate question. Now that you have funding, congratulations, by the way. How long do you think it'll be before you'll extend out your project beyond just these pilot programs to something that the broader AVSO audience could participate in?
Yeah, so we need to try and get this project started. It's one of the conditions of the funding. We try and get this project started in June. it's going to come down to mundane things like how soon I can get my exam marking done, and when I can essentially sit down to find the time to select a group of stars that are really worth following up. So yeah, I would hope to get something out this summer. I mean, we're hoping to start to identify and recruit a research assistant to start this summer, and I'd like them to get started on this as soon as possible. So I would say we definitely want to try and this summer we'll try and get this project started.
Okay, terrific. And I think you're working along with Bert, and so if you need any resources from us, feel free to reach out. We'll be happy to help you.
Thanks for that.
Yeah, Gary was curious. He knows, like with the test project, for example, they share information about exoplanet candidates, and he was curious if PLATO was going to have any kind of like a public release thing that would be similar to what TESS or other exoplanet programs are doing.
They are not, at least not initially. The reason being that because it's a planet survey mission where they're doing the follow-up as part of the mission, the idea is that the access to the light curves is, at least for the prime sample, which are the sort of most promising targets, that's reserved to the PLATO mission so that the best possible follow-up observations can be planned, and that at the point where we actually say, okay, there's a planet with an orbital period of like 250 days and a radius of 1.2 with solar radii going and a mass of whatever it is going around that star, then we're absolutely certain about that. Because as you can imagine, that sort of discovery is going to cause a huge hoo-ha. So at the point where that gets announced, it has to be clear that that is the PLATO mission has claimed it, they've measured it, and they're certain of it. And that all the possible checks and sanity checks and double checks and follow-up observations needed to be absolutely sure of those detections has been done. So for the prime sample, that will be reserved within the project, and there's a lot of organization going on to make sure that the parameters of the planets that are announced by the mission are solid. Now, there are other light curves that will be released. There's a lot of light curves that will be released. Once you get sort of 6, 12, 20, 18 months into the mission, you'll start seeing PLATO light curves appearing. There will be lists of candidates that will appear. People are then free to go and have a look at those candidates themselves. So there will certainly be planet discoveries that are made that are available for follow-up. Those are going to be the shorter period systems. There'll be known planet systems. There'll be things that we're not quite sure what they are, but we don't want to follow them up because they're going to be too expensive. So there will certainly be stuff for people to do. But clearly the prime mission, the Earth twin thing, that's going to take that won't appear for years, and when it gets announced, it will be we're going to be absolutely sure that we found what we said we found.
Okay, and then as our last question, could you remind the audience the first field that PLATO is going to be observing? It will be in the southern hemisphere, but what's the declination range that's going to be covered? Or maybe will any of it be observable from here in the northern hemisphere?
It is quite far south. I'm just trying to think it's probably easier to show you guys this rather than try to describe it. So if I look for LOBS2 PLATO.
Sorry to put you on the spot.
That's okay. What I will do, I will put in the chat for anyone who, I think that's the link. And if I can share my window here, I can show it to you.
I'll repost it here out to everybody.
Yeah, there it is. It's so yeah, the northern edge of this thing is in Canis Major, so it's a little bit south of Sirius. So yeah, for very northern hemisphere observers, like people in Norway and Sweden, I think this is hopeless. But people in places like New Mexico, southern US, may be able to catch the top part of this. The field center is at -47 degrees, and it's at 6 hours 21.
Okay. Yeah, so that is pretty far south for probably most people in the United States, but down in Florida you can see Canopus, so if you're far enough south, you might be able to even catch the middle of the field. So it should be pretty good.
Yeah, I think that maybe this part of the field will be observable from the southern US. Yeah.
Yeah. Yep. Okay. All right. Well, if I could just get you to stop sharing your screen, and I'll go ahead and pull up the outro slides here. All right. So I'd just like to just say thank you one more time to Dr. Maxted for sharing, his time and knowledge today. It's absolutely wonderful that AVSO is getting to engage with Plato, and it's even more wonderful that you're wanting to pull in a citizen science scientist in order to accomplish the work that you're doing. So thank you again very much. I would also like to thank our series sponsor, Voice Astro. They've actually sponsored our entire 2025 webinar series. And so once again, Voice Astro provides online astronomy education, observatory resources, and research experiences for students and schools to perform observations, conduct research, and publish their results. So please check out their website at voice-astro.org. And of course, we cannot forget about the audience here. There were a lot of really great questions, and I apologize, folks, that we weren't able to get to all of them. There were about 10 that we didn't have time to get to today. But if you're more than welcome to forward your questions over to AVSO at avso.org, and we can relay them over to Pierre, and he can answer them in due time. So thank you again for joining today's webinar. It's really helped make this session incredibly fun and exciting. I also saw several questions in the chats about when the video will be posted. So we typically get our videos posted to YouTube approximately within a week after the webinars have been live, just kind of depending on the availability of AVSO staff resources. So if you check out our YouTube channel, you can search for us at AVSO HQ. And then when you leave the webinar today, you should be automatically shown a survey, and I'd really appreciate it if you were to fill it out and let us know what you thought about today's session. We form our webinar series each year based upon the topics and ideas that you all want, and so the more feedback that you can provide us with, the more likely we are to provide something that you find new and interesting. And so our next webinar that we're going to have, which will be presented next month, will be specifically talking about M dwarfs and star spots and transiting exoplanets, and it'll be presented by Dr. Wills Walks. And once again, I'd just like to say, thank you again to Dr. Maxted for presenting today's webinar. And from all of us here at AVSO, thank you, and we appreciate your time. So take care and have a great weekend.